Very much. Hit the right button. It's a pleasure for me to be back here. So thank you very much for the opportunity to speak with you today. As you said, I'm going to be talking about sustainable peace and mathematical models and data science in terms of what I've been doing. And I'm from Queens. So Queens is one of the 5 boroughs of New York City. It's about 10 miles on a side with about 2.3 million people. And it's also a county and is the single most culturally and ethnically diverse county in the entire United States. And this leftover from the 1964 World's Fair is the Unisphere is sort of the unofficial symbol of Queens. And not so far from the Unisphere are these towers from the New York State Pavilion, which I've included here in case there are any fans of the Men in Black movies. So Queens College itself has about 20,000 undergraduate and 5,000 graduate students, and about half were born outside of the United States, and about 600 full-time faculty. And as you heard, I've worked on a number of different systems. This is even only a partial list, actually. But what all these have in common are they're complex systems, meaning they have a lot of individual pieces that interact strongly with each other. For example, physical systems that include motions of stars and gas in galaxies and motions in proteins, biological systems such as gene regulatory networks and the timing of heart attacks, and what I'll talk about today, models of sustainable peace, and also emotional interactions between therapists and their clients in psychotherapy. Well, most research studies on peace have analyzed peace only in a negative way, considering it only as the absence of conflict, violence, or war. But there's a growing effort to understand positive peace, that is, the political, economic, and social systems that generate and sustain peaceful societies. And some of the work that supports this has been done by Douglas Fry and Peter Coleman and Morton Deutsch and Paul Diehl and Gary Gertz and Yusuf Mahmoud. And this is an example from Douglas's Fry work published in Science in 2012, where he goes through a number of examples of peaceful societies. And he discusses at length a little bit about the Iroquois Great League of Peace from New York State, which over a roughly 300-year period managed to maintain a peaceful relationship between 5 and 6 tribes, then later 6 tribes living in New York. And even though there were no wars among these tribes, life goes on as usual. There were murders and crimes, and occasionally they fought wars with people outside. But the group themselves didn't fight with each other. But this was something that was done actively to accomplish this. First of all, there were myths and mores. They had this idea, this symbol of this tree of peace, where cut off below the screen is actually a war club. And the myth was they had buried their war clubs underneath this tree, and an underground secret river had come by and taken the weapons away. And what's interesting about the tree of peace, the bird that sits at the top is an eagle. And in order to maintain peace required eternal vigilance. This wasn't something that happened by magic, but they reinforced this by the myths and mores in the society, by an annual ceremony of peace, by establishing conflict management structures at the village, tribal, and league level at the Council of Chiefs. And interestingly, this is a society where women played an important role. And the women had the right to fire a chief if the chief was behaving badly. So this is part of the Sustainable Peace Mapping Project, which is the Advanced Consortium on Cooperation, Conflict, and Complexity. There's even one more C than you did. At Columbia University. And this is in the 3rd year of a 10-year initiative to use the scientific evidence in a wide range of disciplines to identify the factors that generate and maintain peace, to understand the relationship between those factors. And what my role in this is to turn their qualitative models into quantitative mathematical models, and then to use data science methods to actually measure their proposed piece factors to try to test, improve, and validate those models. And with the hope that maybe we can use this to actually predict effective interventions in systems, and maybe also try to avoid unanticipated consequences. So the group is really led by Peter Coleman, but it includes people from both the US and Brussels and the UK, and there's even a wider group. And the way this process started, they first did a literature review and then conducted a survey where they sent out about 300 survey forms to a very wide interdisciplinary group of people. They got back 72 responses. That led to a small workshop of 15 participants and then a larger workshop with about 50 participants, including academics, practitioners, policymakers in 9 universities, and additional people from the United Nations, the Environmental Law Institute, the United States Institute of Peace, the Inter-American Development Bank, the World Bank, the Omidyar Group, and the Bloomberg Company. And what came out of all this was what is called a causal loop diagram, trying to list what they thought the most important factors were in maintaining peace and how those factors influence each other. So the most important factor, which they unfortunately abbreviated, is positive intergroup reciprocity and negative intergroup reciprocity, which means if someone from another group does something nice to you, do you do something nice in return? And the negative is the opposite of that. They also felt that what was very important were people's emotional historical memory of what happened in the past. How people feel about the past affects how they feel about the present, how they act in the present, and how they feel about the future. And also their expectations of what they expect to happen in the future. And also linked in this are these promotative intergroup structures and processes. So these were the things that kept the Iroquois Federation working and peaceful, and sometimes you can have the opposite effects of those. So these things in red I'll call negative variables because they do things to hurt peace, and I'll call these green things positive variables. And the way things interact, either they reinforce each other, so they have plus signs, or they do the opposite and have a negative effect on something else, and those are indicated by these minus signs. You can also see there are a lot thicker arrows, a lot stronger effects from these negative factors. And that's because when you do something bad to someone, it hurts deeper and longer than when you do something good. So they've been expanding this causal loop diagram to include a larger number of additional factors. So the advantages of a causal loop diagram like this is that it forces people to identify individual elements that they think are important and how those individual elements positively or negatively influence each other. And this also leads to positive feedback loops, which are sometimes called reinforcing loops, and negative feedback loops, which are called balancing loops. And the uses of a diagram like this, it promotes conversation and suggests new hypothesis and theory building. It organizes the available knowledge. It helps to identify potential gaps in current knowledge and policies. And in a diagram like this, you may look for leverage points. To, if you wanted to make something better, maybe that's the point at which you should intervene and change something. Danny Burns from the UK has said that what's important about creating this diagram is not the end point, but the process. So this will usually be done with a group of people in a room, either working on a whiteboard or using Post-its to try to create things. And it's a way of people creating or pulling out of their minds from the discussion with other people what they think is important. So this is an example of that. So this is one of the models that we've been working on. And if there's a change, for example, in normative values, that will have effects on many other things. So there'll be a negative effect on these negative intergroup reciprocities, because it's going to do the opposite of it, and a positive effect on sustainability of things. And the sustainability will have a positive effect on government institutions. And government institutions will have a positive effect on information flow and a negative effect on negative intergroup reciprocity. And if you're nice to PowerPoint, it works without touching it. But negative intergroup reciprocity, as you expect, may have a lot of negative effects on these positive variables. So the limitations of these diagrams are that in principle it might be possible to think through, if you change this, that's going to affect that, which will affect the tertiary set of things, etc. But it's much too complicated to do that. It's very difficult to do that. And also, none of these piece factors have quantitative values. We can't say that something is more important than something else, or something is going to have a bigger influence on something else. And it must be clear that the value of all these things in the system depend on each other. So in principle, we should be able to compute how the value of each variable depends on the value of all the other variables. So we can do that if we create a mathematical model. So in this, we give all the piece factors quantitative values. We have to give quantitative values between the connections of the piece factors. But now we can compute how everything else influences everything else and how that evolves in time. We can also compute what happens when we change something in the system. And part of what we've been doing is to use these numerical equation solvers as a back end of a graphic user interface, which I'll show shortly. And the real advantage of this mathematical model is that it's quantitative. So that means we can use data science methods to measure quantitative values of the piece factor from empirical data. That means we can compare the quantitative values of the model with real quantitative empirical data in order to test and improve and validate the mathematical model. If we can do this, we would hope the model would then have predictive analytics. That is, we can predict the outcomes from proposed intervention and avoid unanticipated consequence. Well, a mathematical model like this also has limitations. We must define the quantitative relationships between these piece factors and how they evolve in time. And we may have, which is the case, only limited data to decide what those relationships should be. So we may have to make uncertain choices at those relationships. And the solutions of the equations might be challenging. And since there's also limited data, empirical data, we may have difficulty finding enough empirical data to compare to the model to see whether the model is really accurate or not. So what's needed to make a mathematical model is we need a quantitative assessment of the strength of influence from one variable to another. We need the mathematical rules of how each variable influence each other and how they evolve in time. And we need clear operational definitions of the variables so that we can actually measure them. So I'm going to show you an example of one of the earlier versions of the central component of this sustainable piece map. So this had 3 positive and 3 negative variables. The positive variables are positive intergroup historical memory, positive goals and expectations, and positive intergroup reciprocity, and the negative values of that. So this is what that model looks like. The blue arrows are positive interactions, the red arrows are negative interactions, and these are those 6 variables. Well, Jacqueline Donahue, working with 3 students at Columbia University, went through 49 articles in the literature to try to see if they could identify these factors in those articles and see if those articles reported connections between the factors. And from that, she did an ordinal estimate of how strong the connections are. First of all, some things are not connected, or things are connected in a low, medium high, or high way. Based on those values, I could assign approximate quantitative values because I know this system has different functional regimes. And I can sort of understand by what they mean by low, medium, and high to choose quantitative values that will represent those different regimes. So this is the actual equations that we use. And it's not as intimidating as it looks, so I'm going to explain what each of the pastel-colored Florida-appropriate colors are in this system. Basically what this term, the first term, says, if the value of a variable gets too big, we're going to cut it down, because otherwise it will go off to infinity. And infinity is not a nice place for us, so we're going to reduce it. But we reduce it proportionately. That is, if it's 100, we make it 90. If it's 10, we make it 9. The second term is a self-stimulatory term. So if you do something good for someone else and they do something good for you, does that make you more likely to do more good things? Or this term could also represent the global effects of those conflict management systems and the other mores that had been put in place by the Iroquois Federation. And this last term is the interaction from one factor to another. And the interaction is done so at low levels, the interaction between the variables is linear, but at a high level, we think there's a range beyond which the variables will not influence each other. And so this hyperbolic tangent function puts a threshold. Another way to explain this threshold is in the olden days in the Bronx, my mother would say to me, Larry, if everyone else jumps off a cliff, are you going to jump off a cliff? And the correct answer was no. And so that's why there's a threshold value here. Okay, I should also say these equations are basically the same equations for what's technically called a recurrent artificial neural network. And in a non-recurrent artificial network, you would have an input and an output, and you would train the system and train the values of these parameters to get the right answers when you put in some inputs. But in this case, we don't know what the right answers are. We don't know what the memories are. We're trying to get these parameters from other things we know from real data. And then it's up to us to explore what memories we've unintentionally created in the system. And we do that by mathematically exploring properties of the system. And what we find in this system, at long times when we evolve it, it only goes to one of two places, which are called attractors. It never winds up in between. All the sets of values of the variables wind up with one set or another set. There's what I call a bad attractor, where the values of the positive variables are 0 and the values of the negative piece factors are large. Or the reverse, there's one good attractor where the values of the positive piece factors are large and the negative piece factors are 0. And what's really interesting is you run this from all different initial conditions. This system, first of all, this is meant to illustrate one way to think about these attractors is we have some energy landscape and things like to run downhill, so they'll stay in an attractor. Even if you move it out of the attractor a little bit, maybe it will fall back in, and there may be other attractors elsewhere in the system.
So it's a gradient system?
A great meaning?
The attractors are equilibrium states?
The attractors would be kind of like energy minimum. It means they're stable critical points.
Yeah.
So you would wind up in them, right? So this is an example of some calculations of that system. The vertical axis are the values of the piece factors, and the horizontal system is time. And in this case, these three values are the bad attractors reach large values, and the positive piece factors are all wind up at 0. And this is meant to illustrate that. So here the size of the circle corresponds to the value of that piece factor at long times. And here you can see the three negative factors have much stronger values than the positive piece factors, which are 0. And this is what things look like in the good attractor, where again, these are the values as a function of time. And in this case, the positive variables, positive piece factors, are larger than the negative piece factors. So this is a computational model. We can play games with it. We can disconnect those negative connections between the positive and negative variables. And if we do that, it's very interesting that the positive variables assume the values they would have in the good attractor, and the negative variables assume the values they would have in the bad attractor. So this is the beginning of a clue as to what's going on here. And in fact, when we run this system for almost all initial conditions, it always winds up in the bad attractor. We have to start it very, very close to the good attractor for it to wind up there. So that's interesting. And why is that happening? Well, it's happening because these negative variables all self-reinforce each other. And then because of this high negative connection to the good variables, they damp them down. So the negative effect, the strong or enhancement, or the fact that negative emotions are stronger than positive emotions, brings this whole system down. Well, we don't think it's always like this. We think we've left something out. And I'm going to describe to you what we think is left out, which is basically that in order to beat these negative emotions, we either add a lot more positive piece factors or we create some crucial piece factors to be much more influential. So I'm going to show you the graphic user interface and show you a little properties of what an attractor actually looks like and some of the other causal loop diagrams that we've been working on. So I'm going to run this program. Those are the class functions. I finally learned object-oriented programming. And this is the program. So this is actually Model 8. And this is what the interface looks like. So this is the same plot I showed you before. These are those 6 variables. And I can point on the calculate button, and if I calculate, it will produce the plots I showed you before of how the variables change in time. Here the 3 positive variables have gone to 0, and the 3 negative variables have become very strong. And the way this is represented graphically is we make the size of the variable names proportional to their values. And so this is a bad place. Well, maybe we can get out of this. Why don't we make the good variables really strong? And then we have a chance of having them turn down what the bad variables are. So I'm going to do that. I'm going to first of all reset the initial conditions. And if I click on a variable name, it will actually pull up the screen on the left, which shows its connections to other variables. So in this case, this negative variable has a very strong connection to the positive intergroup reciprocity. So I'm going to make that 0. And so that arrow is going to go away. And I can increase the effect of the positive variables by making the positive variables have a stronger negative effect on the negative variables. So I'm going to do that by making this -10. Okay. And so this is the new system. And if I now calculate where the system winds up at long time, what you see is these 3 negative variables. There's one here. It's hard to see. It started off higher. It's gone to 0. These 2, because they're self-reinforcing each other, have started off high, but now they're being beaten down by that strong negative influence from the positive variable. And so now we see that the three positive variables are much stronger. So the point of having a tool like this is that you can play with it and try to get some intuitive sense of how the variables are interacting. So what we really want, of course, is to run a model that's a little more sophisticated than that. And this is the model that I showed a little bit earlier. And so this is all those connections, again, blue connections, and they have different strengths, represented as different thicknesses of the arrows, and red are negative connections. And if I calculate this, we'll see where we wind up. And I'm going to click on one of these just to clear the screen a little bit. When I click on one of the variables, it just shows the input and output connections to that variable. So now you can see in this model there are 4 negative variables. They've gotten very small. And what's happened is the larger number of positive variables have now pushed down the negative variables and overwhelmed them, even though the connections between the negative variables are stronger than the connections between the positive variables. Another thing I want to point out to you, an interesting aspect of this model is that the people's memory of the past, positive memory of the past, it's not 0, but it's much weaker than their expectations for the future. That the strongest variables with the largest values are positive intergroup reciprocity and expectations of future goals and values. We're going to come back to this a little bit later. And another model we're running, so that was a model with really a lot of dense connections. Another model which has less dense connections is this one. And let me run this model. And what happens with this model is because there are not a lot of links from a lot of the positive factors into the negative factors, the links go through this sort of gateway or leverage factor, really gateway factor. And the same thing up here a little bit. So even though these positive factors reinforce themselves, they don't really tamp down the negative factors. Well, I said there are multiple ways to fix a system to get it from the bad to the good attractor. I showed you in the previous model, we can add a lot of connections, make a lot of dense connections. In this model, if we change the importance of this factor, which is actually the constructive processes from the Iroquois Federation, if we actually make this more important and have it produce a stronger effect on the negative factors, we can actually get to the good attractor. So I'm not going to show that, but I do want to emphasize that the largest value of all the variables in this model is the negative intergroup reciprocity. And we're going to come back to that also.
Larry, when you have multiple influences that go into a single node, are the influences summed, or is there a function that operates over the individual?
They're summed, but they have that hyperbolic tangent function. So depending on the value of the input, either the effect will be linear or it will reach a threshold.
So the sum of those thresholds is that the thresholding function is applied to the sum of the inputs?
And no, it's applied to each input separately. Okay, so let me get back to the PowerPoint. So what we learned from this is, first of all, we created this graphic user interface. If anyone cares, this is written in Python 3 using tkinter. And we've made this available open source, so it's available on GitHub. We see that the system only has 2 attractors, a bad one and a good one. It has some ups and downs, but it does not have limit cycles or chaos. And it almost always goes to the bad place because the interactions are stronger between these negative factors. But we can make it go to a good place if we add more piece factors, if we increase the effect of certain important good factors, if we self-reinforce positive behaviors, if we have input from the outside that would be equivalent to norms or institutions from other levels. So the importance of this list is that it means in different situations, there are different ways to fix a bad situation. And this is going to be context dependent on how we try to do something. So that's interesting. But the most important lesson here is sometimes a quantitative mathematical model like this can help us see properties of a qualitative model that may not be obvious in the qualitative model alone. So where we stand and where we're going with this, I'll describe how we turn causal loop diagrams into input into the model. We have the numerical equations, and both the formulation and the numerical equations of the models working. We're trying to look at the mathematical properties of the model we've accidentally created to see what they really are. I've already shown you the GUI. And what I want to talk about most next is the data science component of what we're doing. Because we're trying to get quantitative values from empirical data. And we've been looking both at structured data and unstructured data like social network data, and trying to do some other things as well. So the way, as I already said, the way these causal loop diagrams are done by people working together is usually using Post-its or a whiteboard and moving things around and thinking things through. Usually these people are capable of using PowerPoint, and if they can create a causal loop diagram with certain restraints on how things are connected. In PowerPoint, each box like this has 4 connection points, so as long as you do it there and not an arbitrary point, and you can draw lines of different colors and different thicknesses, we've basically written a Python program that converts the PowerPoint into the input files we need for a mathematical model. And the way this works is in 2007, when PowerPoint shifted from PPT to PPTX, they changed how the file format of how PowerPoint is stored. And in fact, if you change a PowerPoint file from extension from this to zip, and at least on the older operating system of the Mac, and double click on it, now you have to go to terminal and do an unzip command. But if you do that, it unzips the single file, and it's not a single file. It's a bunch of files and folders which are all written in XML, and it's all text. And basically what creates this PowerPoint are a series of written text instructions. And if anything, Python is good at parsing text, so you can pull out the names and the location of the boxes and the lines that connect to them and the thickness, and from that we can create the strengths of the interactions between the system that lead to this diagram. So far I've been talking about what I would call a general model, that all of these things I've shown you seem to make sense. They come from people who work in this area, who are scholars or practitioners or policymakers, and we think this has the properties of a complex system. If I push it out of an attractor, it goes back into an attractor. There are bifurcations and a lot of other things that policymakers should understand before they intervene in any system. So that alone has value. But what we're really aiming at is a specific model that has predictive analytics. That is, we want to be able to measure quantitative values of the piece variables and the strengths between them, to compare to get real data into the system and see whether the model really produces a match to the empirical things we can measure. So as I said before, my students, Jacqueline was involved in determining the connections between the variables. Lonnie Schrager has been working to try to understand the mathematical properties of this model in terms of the attractors and when the system goes bad and what factors we can change to change that. one of the things he's been doing is holding each variable, each piece factor fixed at a given value, and then seeing how the rest of the system reacts to that, and doing that at different sets of values. When he does that here, this is a measure of which attractor we're in. It's actually the average value of the positive variables minus the average value of the negative variables. And as he varies one of the factors, this is not loosely connected model, you can see there's a sharp change, phase transition, a sharp change from the bad to the good attractor. On the other hand, for some of the other variables that are less central, in this case, as he changes the value of that variable over a long time, a large set of values, you can see there's a slow, small change in that variable, but it doesn't flip it to the other attractor. So what we're doing by trial and effort is to see which are the most important things to change to push the system into a different place. My colleague Lev Guzman-Vargas in Mexico City has been approaching it a different way. There are a lot of theories and mathematical tools we can use to analyze networks. So he's been looking at functions like betweenness that define different communities, which identifies this pronorms factor and this constructive processes factor as being particularly important. And you don't need a computer to do this either. If you were doing this entirely qualitative, you would think these two factors play an interesting role in this system. So there are a number of ways to change to determine either theoretically or by trial and error which are the most important elements in the system in affecting the whole system. And to shift into full jargon, but for very briefly, I'll tell you when it's over. Another analysis he's been doing is to look at the components of the eigenvector of the largest eigenvalue. And that's over. Because that component with the largest value should be the value of that variable at long times in the attractor. And in fact, that's true for this system. That analysis predicts this system that negative reciprocity should have the largest value. And that's actually true. But this analysis does not work for the densely connected diagram. And in fact, most of these analyses of networks usually assume the connections are either there or one. And here we have a system where the connections are either positive or negative, and they have different strengths. So we don't really have the mathematical tools to do the analysis here the way we would really like. But that's good. So that means either someone else or us will develop a better mathematical tool that will have applications to here and other networks. Chaim Eisenbach has been looking at databases. One of the ones that is most used is the Global Peace Index to measure some of the variables. And it turns out this seems simple in principle. In reality, it's not. He found that drilling down to see where the data actually comes from, sometimes an element in a database comes from a real identifiable source, like a census data or something like that, or health records. But sometimes it leads to things like some of the things in the Global Peace Index are from an unspecified number of people on a committee for The Economist magazine. And they're rating the internal violence in a country between 0 and 5. And maybe they're getting it right even, I don't know. And sometimes he drills down, you can't even figure out where the data has come from. And sometimes, as shown here, the data is actually circular with databases using data from each other and reaching at different levels. So this isn't as simple as it seems. Mohammed Salimi and Ahmad Khan have been looking to measure intergroup reciprocity. So they've been looking at fans of football teams, what you would call soccer, and in both London and in Northern Ireland. And they can identify them by the hashtags they're using about the team, and then they're looking for other hashtags that the same people use. And in this case, they were looking to see whether fans of the same team use Britain First or Refugees Welcome, which are sort of opposite websites supporting or opposing refugees. In fact, we had, what they found actually is most of the teams, maybe not Arsenal, but actually had a pretty good components of people from both groups, which is actually healthy. So that's interesting. The bottom graph is they're also looking at UK census data to see what the ethnic makeup around the stadiums was. And Adina Beckhofer has been looking to try to measure positive and negative historical memory and intergroup future goals and expectations. So she defined a series of about a dozen words or more that people would use talking about the past or talking about the future. And then she could find tweets with those words and then do a sentiment analysis on the rest of the words in the tweet. So sentiment analysis means you try to measure the emotional valence. That's my psychology word for today and yesterday is valence. And you can measure there are databases to measure the emotional valence to try to get an estimate about whether someone is expressing a positive or negative emotion in the tweet. The first thing we found from doing this, which surprised both of us and the rest of my group too, on average, most tweets are actually slightly positive. I'm not on Twitter, but I would think from what I read on my mass media that everything's awful on Twitter, but actually it's sort of slightly positive. And when it's negative, on average, it's not very negative. But besides that, what you did find is that the positivity of the future was greater than the past, which were greater than the average positivity in random tweets. And this was statistically significant, but we found that this changes over time. So in fact, this was done just around or before New Year's. Maybe people were feeling more positive about the new year. After this, this has changed a little bit. So this is a nice measure, but it also changes with time. If you remember when I mentioned before, on one of the models, people's future expectations had a higher value than their past. And that's because there are more things connect to the future than the past. You can't do too much about the past. And so in those models, for that reason, unintentionally, would predict that these future expectations would be higher than people's emotions about the past. Douglas Fry has been going through primary anthropological sources, identifying 25 factors and maybe a dozen or 20 subfactors of those. And we've been looking at that. They haven't finished doing the coding, which are done by real live human beings. And we've been gearing up to do either a multi-element logistic regression or machine learning on that to see if we could identify the factors. He has two groups, one of societies and cultures that are peaceful and one that aren't. We're trying to see if we can pull out from this data what are the characteristics of peaceful and not peaceful societies. The other thing is everything I've been describing now is a top-down approach. The original groups sat down at a table and drew boxes and arrows, and we turned it into a model, and we looked for parameters of the model. But it's all top-down. In data science now, there's a different approach where you don't start with what you expect, but where you start with the raw data and do things on the data to try to assemble what you think is going further up. So we've been working with David Bly, who's at Columbia, to try his topic analysis, which is a way of looking at individual words within context to then see how things combine together and how they group into larger topics. And they've been doing this actually on things like biomedical research to see how different genes and different things influence each other. I think he's currently working with someone in the history department at Columbia doing this and analyzing diplomatic cables. So the conclusions of this is peace is not just the absence of war. It needs a positive peace system and strong negative emotions that would put the system in a bad place can be overcome in a number of different ways, by a set of many good factors or by a few strong, well-placed placed factors. And this is situationally dependent. Then it may be in different situations, different piece factors or different ways of supporting the system may play the most important roles. Another part of the conclusion is that mathematics can be our friend. A lot of the social scientists are not convinced of that, but it's true. We can do things that help us bring additional insight. They don't replace, but they bring additional insight into the qualitative models. And we do this by encoding our assumptions into equations, solving those equations, seeing the results, which do sometimes surprise us, and comparing those results to data. And to help people do that who don't have as much computer experience, we've created a user interface to make that a little bit easier. And as you're already told, a lot of this is on our website. There's some of the piece articles. In blue here is part of the reason why I'm here, which is working with Paul Peloso on analyzing the data he's been collecting on interactions between therapists and clients and psychotherapy, a number of other publications. Toward the top of the website, there are a number of videos that explain some of the stuff I've been doing. And also, I've been teaching mostly physics courses. So we had a physics course we taught for computer science students. I didn't think it was that up to date. So over the last 2 years, I've been working to update it. And that course has a lot of more modern physics and how it affects computer science, like quantum computers and things like that. And all of the lectures from that course, not the recitation problems, but at least all of the lectures from that course are on YouTube. And there's a link to that from my website also. Thank you.
So Larry, we've had a couple of questions. I'm sure we've got.
Wait, let me just do this.